Welcome to our next video in the series on condensed matter theory. In this video and in the next video I want to talk about the temperature dependence of the chemical potential. In this video we will give an analytical expression of the integrals that we encounter, and in the next video we'll go a bit more into it because the analytical expressions are in the end not very intuitive. When we look at the number of particles that we have and we want to express them in terms of the densities of states and the Fermi-Dirac distribution, which depends on the chemical potential, then we know that an integral over the densities of states times the probability to have a state at that energy occupied integrated over all energies must be equal to the total number of particles. And our Fermi-Dirac distribution is given as 1 over 1 plus e to the energy minus the chemical potential divided by k Boltzmann T. So if we look at our Fermi-Dirac distribution, then at the chemical potential, for T equals 0, it just goes from 1 to 0 at the chemical potential. And at larger temperatures, this is a function where you lose occupation below the chemical potential and you gain occupation above the chemical potential. And the function is symmetric, such that the volume here is equal to the volume there. So we can ask the question, why is our chemical potential a function of the temperature? And for that we have to realize that the number of particles needs to be conserved in our system. Let's have a look at an example before we will derive the chemical potential or the temperature dependence of the chemical potential in the Sommerfeld model. But there is actually a reasonable intuitive way to understand why the chemical potential has to be energy dependent and how it should change. So as an example, we'll take a densities of states that is a constant plus a linear dependence on the energy. If you're in a small enough range around the Fermi energy, that is always a good approximation. So we have our energy and the Fermi energy, and our densities of states is some linear function. We can look at the Fermi function at t equal to 0, which goes from 1 to 0, such that t equal to 0, the occupied densities of states, is a straight line up to the Fermi energy, and then it drops to 0. We can now have a look at the Fermi function as a function of energy at the chemical potential that is equal to the chemical potential that you find at 0 temperature for temperatures larger than 0. It is a half at the Fermi energy and has a symmetry around the Fermi energy. Such that probability that you lose below the Fermi energy, you gain at an energy above the Fermi energy. The occupied densities of states at t equals 0 is given as the densities of states times the Fermi function at t equal to 0. If we now look at the occupied densities of states at a finite temperature, and we would take the Fermi-Dirac distribution at the same chemical potential, then we see that below the Fermi energy we have a small densities of states multiplied with a probability to occupy it, so we lose here some states. And above the densities of states we now have the probability that we lose here coming back here, but multiplied with the larger densities of states. So if we do this and we keep the chemical potential constant, then one would find that the total number of particles increase. So if we look at the densities of states and multiply it with the Fermi-Dirac distribution, at the chemical potential we have at 0 temperature, at temperatures larger than T than 0, we find an increase in particle number. Well, and that is not allowed, so what we need to have is that the chemical potential at finite temperature is smaller than the chemical potential at 0 temperature, such that the Fermi-Dirac distribution shifts slightly to the left and the total number of particles is conserved. We can make a reasonable general statement. If the derivative of the densities of states at the Fermi energy is larger than 0, then our chemical potential at finite temperature is smaller than the chemical potential at 0 energy, which is the case that we have here. The other way, if our densities of states, the derivative of the densities of states at the Fermi energy is smaller than 0, we haven't explained yet how this can happen, but we'll show in later lectures that this will happen, then we find that the chemical potential at finite temperature is larger than the chemical potential at 0 temperature. With this knowledge, you can now actually explain how things like Peltier elements work, where you connect two metals. One side you make the connection cold, the other side you make the connection hot, and then a current starts to flow, which is something you can use to generate electricity from heat differences or excess of heat. And what you do in these materials or in these systems, you take two different materials, one with a positive slope of the densities of states at the Fermi energy, and one with a negative slope of the densities of states at the Fermi energy. And this then will generate a voltage when you make these connections at a different temperature. And you can try to puzzle and see if you can understand why that happens. And if not, we can discuss. So, what I want to do in this lecture further is have a look at the temperature dependence of the chemical potential in the Sommerfeld model. And again, we start with the boundary equation that our total number of particles must be conserved and is independent of temperature. We have our densities of states, which is a normalization 2m over h bar squared to the power 3/2 times the square root of the energy, the Fermi function that we've seen before, 1 over 1 plus e minus mu divided by k Boltzmann T, and the number of particles. And instead of just looking at the density, we can actually express this in terms of the Fermi energy, so that we see the change of chemical potential as a function of temperature, and this is 2m the Fermi energy divided by h bar squared to the power 3/2. And these are the equations that we had in previous lectures. in the series on Sommerfeld model. We can fill in these three equations for the densities of states, the Fermi function, and the density of particles. And what we get is that the integral over the square root of the energy divided by 1 plus E minus mu divided by K Boltzmann T, and I just took all the constants to the other side of the equal sign, is 2 over 3 pi times the Fermi energy to the power 3/2. Now this integral, we all know, which is the Pauli logarithm. If you take this integral and you take out one of your books with standard formulas, then it's definitely in there. Or you take Maple or Mathematica and you type in this integral, Wolfram Alpha, you type in this integral and it will tell you that it's a Pauli logarithm. And what this says is the Li N E is basically that this is an important integral, and that's why we've given it a name, and that there is no simple solution of this integral in terms of other standard functions that we know. So we cannot just say that it's a simple function of some sine, cosine, logarithmic functions, etc. So we have given it a new name. And if we then use the Pauli logarithm, then we find a dependence, and it is the Pauli logarithm with n is 3/2, and the functional is e to the power mu over K Boltzmann T, and that is 2 over 3 pi EF to the power 3/2. Well, we want to calculate mu, so we have to take the inverse of the Pauli logarithm and then the logarithm of that. So our chemical potential is K Boltzmann T, the natural logarithm of the inverse of the Pauli logarithm with n is 3/2 of minus 4/3 K Boltzmann T over pi to the power 3/2 and your Fermi energy to the power 3/2. Given this analytical expression, it's not so trivial to see what the behavior of your chemical potential as a function of temperature is. Especially as we know that at T equals 0, this has to be the Fermi energy, whereas here you have this T going to 0, but the logarithm of the inverse of a Pauli logarithm goes to infinite, and such that the limit will go to the Fermi energy. But of course we can use our computers to make a plot of the chemical potential, and we do this in units of the Fermi energy. We have 0, 1 as a function of temperature in kBT. And when your temperature is 0, the chemical potential is the Fermi energy. And then when you increase the temperature, it starts to decrease. And at the Fermi energy, when your temperature is equal to the Fermi energy, the chemical potential drops to 0. And at 0 temperature, the chemical potential is your Fermi energy. What you also see if you make a plot is that the derivative of the chemical potential with respect to the temperature is 0 at 0 temperature. So at very low temperatures you can neglect that there is a dependence of the chemical potential as a function of temperature. And as we have predicted before, we have a function, the square root of E, that increases as a function of energy at the chemical potential, so a positive slope. So the chemical potential becomes smaller with an increase of temperature. So if we look at our densities of states in the Sommerfeld model as a function of energy, that is a square root of the energy. Then at zero temperature, we can look at the occupied densities of states as a function of energy, which follows the densities of states up to the chemical potential at t equals 0, and then become 0. So these are the occupied states. And then at finite temperature, the occupied densities of states is a product of the Fermi function times the densities of states, but our chemical potential is no longer at the Fermi energy, but lower. And I think I'm exaggerating here, but that's okay. And these are then the occupied densities of states at finite temperature. And the volume that you're missing here is the volume that should come back there, so that the total integral is conserved, which is the total particle number. And there you can see that I reduced my chemical potential too much in the plot as a function of temperature. But if I would have kept it the same, then the total number of particles would have increased. So you have to reduce it a little bit. Very good. So in the next video, I want to discuss a bit more intuitive but approximate analytical solution for the temperature dependence of the chemical potential in the Sommerfeld model, because the logarithm of the inverse of a polylogarithm is not really a function that tells you a lot, unless you make a plot. And well, most computers or graphical calculators that you have should be able to make those plots, because a polylogarithm is a very common function in statistical physics or in mathematics, but not one that we are really used to and know all the properties of. Thank you very much for your attention. Stay healthy. We see each other in our next video.